Good evening, everyone. Today we are going to solve two other example problems for sensitivity analysis. And the first example is about the ice cream company problem. Like it says, Ken and Larry Incorporation supplies its ice cream parlors with 4 different flavors of ice creams. They are chocolate, vanilla, banana, and strawberry. I'm not quite sure what's the big difference between the vanilla and the banana ice cream though. Anyhow, because of extremely hot weather and a high demand for its products, the company has run short of its supply of ingredients such as milk, sugar, and cream. Okay? So they will not be able to fill all the orders received from their retail outlets, the ice cream parlors. Owing to these circumstances, the company has decided to choose the amount of each product to produce that will maximize total profit, given the constraints on supply of the basic ingredients. Okay? And the chocolate ice cream requires 0.45 gallons of milk and half pounds of sugar and 0.1 gallons of cream. And vanilla ice cream requires half gallons of milk and 0.4 pounds of sugar and 0.15 gallons of creams, and so on. And the company has only 185 gallons of milk and 165 pounds of sugar and 65 gallons of cream left in its inventory. Okay? And the chocolate, vanilla, and banana and strawberry flavors generate respectively $1.90, 95 cents, and 85 cents per profit per gallon sold. Okay? So we have an LP formulation for this problem like this, because the primary decision is how much of each flavor of ice cream should be produced. We have 4 decision variables, C, V, B, and S, representing the gallons of chocolate, vanilla, and banana, and strawberry ice cream produced, respectively. Okay? And our objective function is to maximize profit subject to 3 resource constraints and non-negativity restrictions for each decision variables. And I've got this LP formulation from Lindo. You remember, Lindo assumes every decision variable used in the models are non-negative unless specified otherwise. So in here, the non-negativity restrictions are omitted. And if you use Lindo to solve this problem, you may obtain the optimal solution and some additional information for sensitivity analysis, and the final optimal table like this. Okay? And we are required to answer the following 10 questions. The first question is the optimal solution above degenerate? What is the answer? What is degenerate solution? I said for any basic variable, if at least one basic variable has a 0 value, then we call it degenerate solution, right? And when this occurs, the next basis change may not result in an improvement in the objective function value, right? So does our optimal solution degenerate? So if you look at the optimal solution, how many basic variables do we have in this example problem? 3, right? C has a positive value, and V has positive value, and S has positive value. And all others are 0, right? And how many constraints do we have? We have only 3 constraints, right? So we should have 3 basic variables, 1 for each constraint. So this is not the degenerate solution, right? Okay, the next question. The number of basic variables in this optimal solution is how many? We've already answered this question in question number 1, right? We have 3 basic variables in the optimal solution, 1 for each resource constraints. And again, there are 3 positive variables in our optimal solution. They are C, V, and S, right? Okay, next question is, suppose the company discovers that 2 gallons of cream has gone sour. So they must be thrown out. Then what happened to the optimal objective function value? Reduce? Okay, let's see. So currently the company has only 65 gallons of cream left in their inventory, right? However, 2 gallons of them must be thrown out, right? And here, the row number 4, the last row, represents the cream resource constraints, right? So this question asks, what happened to the objective function value if the right-hand side value of 65 is decreased by 2 units? Is this correct? So what window information you need to look at? Dual price. That is correct. So what is dual price? Like it says, dual price is the amount by which the objective function value would be improved given a unit of increase in the right-hand side of the constraint. However, you remember this definition of dual price applies only if the change in the right-hand side of corresponding constraints leaves the current optimal solution remains feasible, right? Which means the dual price remains valid within these allowable right-hand side ranges. Is that correct? And in our example, the optimal solution report provided by Lindo includes these right-hand side ranges. So you need to look at this value. Allowable decrease limit for the last constraint, right? And the decreasing 2 gallons of cream is still within the allowable decrease limit of 13.75 gallons. So the current due price for row number 4 are still valid. Is that correct? And in our example, the optimal solution report provided by Lindo is like this, which means the objective function, that is the profit, will increase 1.292517 per unit decrease in cream, right? And because because 2 gallons of cream will be decreased, the profit will be decreased by 2 times this much, right? Your price, 1.292517. Additional minute of available time on the machine number 1, right? So what is this value? It's going to be 2.585 approximately, right? I said the due price indicates the improvement in the objective function value resulting from a unit increase of the right-hand side value, right? Okay, next. Number 4, to adjust for the loss of 2 gallons of cream, what should be the change in gallons of vanilla ice cream to be produced? So how would you answer this question? We know the last row, last constraint, is about the cream resource constraint, right? So, by introducing the slack variable, this row number 4 becomes the following equality constraint: 0.1c, 0.15v, 0.2b, 0.18s plus slack 4 equals 65, right? And currently, slack 4 is 0, right? At the optimal solution. So slack 4 is 0, which means all other terms on the left-hand side becomes 65 to maintain the equality constraint, right? And to determine the effect on the production plan of decreasing the amount of cream by 2 gallons, we must increase the slack variable 4, number 4, which is the unused amount of cream, from 0 to 2 gallons, okay? So the revised solution would be this whole part becomes 63, right? To maintain the equality. Is that correct? Okay, then what's next? We need to look at the substitution rate, right? And the substitution rate, alpha ij, which is this, indicates how much the basic variable x of I in row number I, right, decreases as the non-basic variable x of j increases. Okay? So 1 unit of xj variable substitutes for alpha ij units of the basic variable in the optimal solution. And here, the substitution rate of slab variable 4 for vanilla ice cream is negative 15.646, right? So how would you conclude from this? As slab variable number 4 increases by 1 unit, the basic variable, which is v, will decrease by this much. Okay? Which means as slab variable number 4 increases 1 unit, the basic variable, which is v, increases 15.646. Is that correct? Because decrease negative 15.646 the same as increase 15.646, right? So to adjust for the loss of 2 gallons of cream, the change in gallons of vanilla ice cream to be produced should increase by 15.646. Okay? That's the answer. Any questions?
Times 15 or just 15
Oh, yeah, times 2, right? Sorry. So it's going to be, because slab 4 has been increased by 2 units, right? So the increment of basic variable v must be multiplied by 2. Okay? Thank you for finding an error. Okay, next, number 5. If it were required to make 10 gallons of banana ice cream, what will be the cost in doing that? to answer this question, what information you need to look at? Reduced cost, that's correct. What is the reduced cost? The reduced cost of a non-basic variable is the rate of deterioration of the objective function as the variable is forced to increase by a small amount. Okay? So, in a maximization problem, just like our example, the reduced cost gives the rate of decrease, right, in the objective function value. However, the minimization problem, it gives the rate of increment in the objective function, right? And I said the reduced cost of a basic variable is always 0, right? And in the optimal solution, the B, which is the banana ice cream, is 0, which means variable B is non-basic variable, right? And the corresponding reduced cost is 0.007823, right? So, which tells us the profit will be reduced by 10 times this reduced cost, right? So, if you produce
we need to shift the ranges, yeah. The yellow will increase.
No. We are talking about the value of decision variable, right? So when you deal with the objective coefficient or the right-hand side value, then you need to look at the allowable ranges, right? But not this case.
We are going to increase the number of gallons for bananas.
No, we are talking about number 5, right? So if you produce 10 gallons of banana ice cream, which means if you want to have the value of B to 10 from 0, okay? Then your profit will be reduced by 10 times this much, right? Is that correct? Okay, next question is number 6. If it were required to make 10 gallons of banana ice cream, what will be the effect on the production of chocolate ice cream? So what information you need to use to answer this question? we've learned substitution rate alpha ij indicates how much xi variable decreases as non-basic variable xj increases, right? So for example, in this table, currently the value of xi is, let's say, right-hand side of subscript I. Okay? Then if xj, that is the non-basic variable, is increased by 1 unit, then this basic variable xi becomes the current value minus this substitution rate, right? Is that correct? What if xj is increased by 2 units? What happened to xi? If xj is increased by 2 units, then xi becomes current right-hand side value minus 2 times this, what is that, substitution rate. Does that make sense? So, if the non-basic variable B increases by 10 gallons, using the final optimal table, we may answer the question. So you need to look at the substitution rate for this, right? So if the non-basic variable B increases by 10 gallons, then the basic variable C becomes, the current value is 110.204, right? 110.204 minus this substitution rate 490 times the B value with a value of 10 for B, right? So this becomes 110.204 minus 4.9, right? Which means the production of chocolate ice cream would decrease by 4.9 gallons. Does that make sense? Okay, next is question number 7. How much must the profit of chocolate ice cream drop before its production would be decreased? So what window output you need to look at? I'm sorry?
The gel price.
Could you say that?
Asking which window output we need to look.
Uh-huh.
Yeah, I would say the gel price.
How dual price?
Yeah.
Why do you want to look at the dual price for that? Okay. Let me first explain it. And then if you still have the question, then please let me know. Okay? We need to look at the objective coefficient ranges first. Because the objective coefficient ranges in Lindo output indicates the amount by which the objective coefficient can be increased or decreased without causing a change in the basis, right? And according to the Lindo report, the allowable decrease of chocolate ice cream is 0.015972. This means that within this decreased limit of objective coefficient of variable C, the optimal basis is unchanged. Okay? However, for example, if the profit of chocolate ice cream drops by 2 cents, 2 cents is $0.02, right? Which exceeds this allowable decrease limit, then the optimal basis will be changed, which means the production plan will be changed. Of course, the production of chocolate ice cream will be decreased because the unit profit has been decreased, right?
So we are decreasing the amount we are producing or the profit.
Yeah, I think the question is maybe how much production.
Yeah. Because here it's like
can be decreased before the profit.
How much must the profit of chocolate ice cream production would be decreased? So the answer is this.
so we are decreasing the profit. Oh, okay.
Right?
Yeah.
So the answer is $0.015972.
So
Right?
7 is not related to what we are doing.
No.
Oh, I see. Yeah, that's fine. Yeah.
Okay? Okay. Thank you.
It will decrease 2 times
2 times?
2 cents there.
No. Well, it just asks the ranges, right? So you don't need to multiply any numbers at this moment, right? Probably you are looking at other questions.
No, just
No, is that okay? Okay. So is that clear right now?
the answer is
$0.015972. Okay? I know the question is a little bit twisted, right?
no, but it's okay.
Okay. Thank you too. Okay, next question is number 8. If the profit of strawberry ice cream were to be 88 cents per gallon, what will be the effect on the production of strawberry ice cream? Does the production of strawberry ice cream would increase, decrease, or remain the same? Or cannot be determined? What is it? So what Lindo output we need to use to answer this question? Okay, so the profit of strawberry ice cream has been changed to 88 cents per gallon from 85 cents per gallon, right? This change means an increase of 3 cents in the objective coefficient of the variable S Is that correct? So, you need to look at the objective coefficient ranges first. According to our Lindo output, the allowable decrease is that increase? Oh yeah, thank you. Allowable increase for strawberry ice cream is 0.007143, right? So the 3 cents, which is $0.03, exceeds this amount, right? And the optimal objective coefficient ranges, which means the basis will change, right? And it seems clear that the basis change would result in an increase in the production of strawberry ice cream, okay? Because it will give you more unit profit than before. So, if the profit of strawberry ice cream were to be 88 cents per gallon, the production of strawberry ice cream would increase, right? But we don't know how much it would be exactly. It will just increase, right? Okay, next is number 9 and number 10. I think to answer both questions number 9 and 10, you need to build up a dual LP. The given LP is maximization problem with less than equal constraints and non-negativity restrictions, right? And what is that? It is in the form of primal dual pair. It is in the form of dual in the symmetric primal dual pair, right? So this dual must be a minimization problem with greater than equal constraints and non-negativity restrictions, right? And because the primal problem has 3 constraints, which means the dual problem must have 3 decision variables.
And there's supposed to be milk sugar.
Sorry?
These variables are going to be for milk, sugar.
Oh, yeah, the price for that, right? Right. Okay. And let's use the y variable as a dual variable, okay? Then our dual problem becomes minimization problem, and we must have 3 decision variable, right? And because we have 4 decision variables in the primal problem, which means we will have 4 constraints in the dual problem, right? Oh, this must be 2. And the objective coefficients are 1, 0.9, 0.95, 0.85. So the transpose of this vector becomes the right-hand side value, the dual problem, right? So it's going to be 1, 0.9, 0.95, 0.85, right? The right-hand side value, 185, 165, and 65 becomes the objective coefficient in the dual problem. And the transpose of constraint coefficient becomes the constraint coefficient in the dual problem, right? So this is going to be like this, 0.5, 0.4, 0.4, 0.35, and 0.1, 0.15, 0.2, 0.18, right? And we have all positive signs. And we have greater than equal signs, right? And all the variables are also non-negative. So we have dual problem like this, right? So, first, question number 9. The number of variables in the dual of this LP problem, except for z, objective function rho, is 3, right? It's pretty easy. What about number 10? The sign restrictions on the dual variables are all non-negative. It's very easy, right? So, any questions about this ice cream company problem? Okay, if you don't have any questions, then let's consider another example problem, which is about stone cutter company problem. So, the classic stone cutter company produces 4 types of stone sculptures. They are figures, figurines, and freeforms, and statues. And each product requires the following hours of work for cutting and chiseling stone and polishing the final product. The company's current workforce has production capacity, which is sufficient to allocate 300 hours for cutting and 180 hours to chiseling and 300 hours to polishing each week. Okay? And each figure sells for $280, figurines $40, freeforms $500, and statues $510. Okay? And because the primary decision is how many of each types of stone sculptures should be produced, we define the decision variables like this. Let's say figure is the number of figures to be produced each week, and figurines, there is the number of figurines to be produced, and freeforms, number of freeforms to be produced. Likewise, statue represents the number of statues to be produced each week. Okay? then we have a complete LP formulation for this example problem like this. And our objective function is to maximize profit, right? Subject to time constraints for 3 departments, okay? Cutting and chiseling and polishing department, for example. And non-negativity restrictions for each decision variables, okay? And I've got this LP formulation from Lindo. Again, just to let you know, the non-negativity restrictions are omitted here. And if you use Lindo to solve the problem, you may obtain the optimal solution and some more informations used for sensitivity analysis. And finally, you may obtain the final optimal table like this. Okay? And we are going to use all this information to answer the following questions. Okay, the first question is, I think, is the same questions, right, that we have for ice cream company problem. Is the optimal solution degenerate? How many constraints do we have? You have only 3 constraints, which means you must have 3 basic variables, right? Obviously, 3 variables has positive value: figure and statue and slack variable for the last constraint, right? So this solution is not degenerate. Okay? What about number 2? The number of basic variables in this optimal solution is 3, right? 1 for each constraint. And again, they are figure, statue, and slack variable number 4. Okay? What about number 3? In any basic feasible solution of this problem, which of the following is correct? If you look at the formulation, because the number of products is greater than the number of basic variables, right? So what is the answer? A. Not every product will be included. Is that right? That was the simple question. Okay, what about number 4? If it were required to make one freeform as a salesman sample, what happened to the profit? What happened to the objective function value? So what information you need to look at? You remember the reduced cost of a non-basic variable is the rate of deterioration of the objective function as the variable is forced to increase by a small amount, right? And I said the maximization problem, the reduced cost gives the rate of decrease in the objective function value. And in the optimal solution, currently the free form is 0, right? Which means the variable free form is non-basic variable. And the corresponding reduced cost is 70, right? Which means the profit will be reduced by this much, right? So if you make one free form as a salesman's sample, then your profit will be decreased by 70. Okay? Any questions? Okay, what about number 5? If it were required to make one free form as a salesman's sample, what will be the effect on the production of statues? We know the substitution rate alpha ij indicates how much xi variable, that is the basic variable, decreases as xj, that is the non-basic variable, increases, right? So if you make one free form as a salesman's sample, using the final optimal table, we may determine the effect on the production of statues. Okay, here's the free form, and statue is right here. So the substitution rate is -3. And currently, the value of statue is 2, right? So the statue becomes 2, which is the current value, minus -3, that is the substitution rate, times the value of free form. The value of free form is 1, right? It's going to be 3 plus 2 plus 3, right? So the production of statue would increase by 3 units. Okay? So everyone following me? Okay, next is number 6. This is the multiple choice problem. So, if it were required to make one additional statue, the profit will decrease by how much? And you are required to choose the nearest value. So again, you need to look at the reduced cost. Okay? And the reduced cost is defined for non-basic variable only. Okay? That's the key point for this problem. Currently, the statue is a basic variable since it has the positive value, right? And according to the definition of reduced cost, because, like I said, reduced cost is defined only for the non-basic variable, we cannot say anything. Okay? So, what is the answer? The answer is J. Cannot be determined. Okay? Okay, next is number 7. It's not too fast, right? Is that okay? Okay. Number 7, if the profit of freeform were to be $600 per unit, what will be the effect on the production of freeforms? So we need to look at the objective coefficient ranges, right? So what value we need to look at? The allowable increase limit, right? For freeforms, right? Which is 70. So $100 of increase exceeds the allowable increase of 70 in the objective coefficient ranges, right? Which means the basis will change, okay? Of course, it's going to be increased, right? So, if the profit of freeforms were to be $600 per unit, the production of freeform would increase. Okay? Okay, next is question number 8. If 10 additional hours of chiselings were available, what happened to the objective function value? Your price? Okay. So, according to the problem description, the company's current workforce has production capacity, which is sufficient to allocate 180 hours of chiseling, right? And here, row number 3 represents the time constraints for chiseling. So what happened to the objective function value if 10 additional hours of chiseling were available if right-hand side value is increased by 10 hours. So you need to look at the dual price, right? However, again, the dual price remains valid only if the change in the right-hand side of corresponding constraints leaves the current optimal solution remains feasible. So, first of all, you need to look at the right-hand side ranges. Okay? Increasing 10 hours of chiseling is still within the allowable increase limit of 20, right? So the current dual price for row number 3 remains valid. And in our example, the dual price for row number 3 is 5, which means the objective function, that is the profit, will increase $5 per additional hours of chiseling. And because 10 additional hours are available, the profit will be increased by 10 times this much, 5, right? So the profit will increase by $50. Okay? It's not that difficult, right? But you should be careful. Okay, what about number 9? If 10 additional hours of chiseling were available, what's the effect on the number of figures? We know the row number 3 represents the constraints for chiseling, right? So, like we did before, by introducing the slack variable, we will obtain the equality constraint, like this. Figure 8 times figure in plus 60 freeform plus 30 times statue plus 3 equals 180, right? Should use different color. And to determine the effect on the production plan of 10 additional hours of chiseling, we must decrease the slack variable, slack 3, that is the unused hours of chiseling, from 0. That is the current value for slack 3, right? To negative 10, right? because current optimal solution, this value is 180, but the revised solution becomes 190, right? And then you need to use the substitution rates. There is the final optimal table, right? Again, 1 unit of xj variable substitute for alpha ij units of the basic variable x of I. Okay? So here, the substitution rate of slack 3 for figure is 0.2, right? So how would you conclude? As slack 3 increases 1, the basic variable figure decreases 0.2, right? Which means as slack 3 decreases by 10, the basic variable figure increases by 10 times 0.2. So if 10 additional hours of chiseling were available, the number of figure would be increased by 2. Okay? Is that clear? Okay, then this is all for today. And next time, I'm going to finish up this example and give you another example problem for sensitivity analysis. Okay? Thank you. I will see you next time. Bye.